Hi there. So in this video I'm going to talk about the bi-orthogonal transformations, and I'll take Taylor series as an example. So first of all, I'll try to review the orthogonal transformations. The Fourier series actually represents a perfect example of orthogonal transformations. Now, the Fourier series represents a perfect example of this kind of transformations, where we assume that a function like f of x can be decomposed or reconstructed by adding up a scaled kernels from some family like k f naught. So this is the family of kernels. Let's just define it by e to minus j 2 pi k f naught x, where k runs from 0 to infinity. And here we got a family of kernels. Now each and every single member of this family is going to be multiplied by a coefficient. And when we add up all these scaled members of this family, we'll get f of x. Now the thing special about this family is the orthogonality. Like if we just substitute k equals 0, we get 1, and when k equals 1, e to minus j 2 pi f naught x, when k equals 2, e to minus j 2 pi dot 2 f naught x. And if we substitute k equals 3, e to minus j 2 pi 3 f naught x. So the special thing about this family is that each and every single member of the family is orthogonal to each and every single other member of the same family. So except for itself, of course, a function cannot be orthogonal. So that is the review of the orthogonal transformations, and if you are already confused or you don't know what I'm talking about, you're recommended to watch my Fourier series video. I'll give you the link in the comment section down below. Now, going forward to Taylor series, and I'm presuming you're familiar with Taylor series, which states that a function f of x can be expanded in this form: summation an, a coefficient, times x to power n. So this is the kernel x to power n, where n runs from 0 to infinity. And this is the family. If we're expanding, x to power 0 is 1, and then x squared, and then x cubic, then... But the thing obvious here is that there is no orthogonality between the members of this set. For example, let's just find the correlation between x and x cubed. So integration from minus infinity to infinity, x to power 1 dot x to power 3 dx. And it's pretty much obvious that the result diverges to infinity. And it's also obvious that there is an infinite correlation between 1 and x squared and x to power 4. So how does the Taylor series works while this set lacks this fundamental property of orthogonality? Well, I've recently discovered that it's working according to the bi-orthogonality principle, as I shall prove in this video later on. Now I'd like to tell you how a bi-orthogonal transform works. So it says, if you have a signal f of x, it can be expanded by this summation, let's say over n, alpha n, a coefficient, then a kernel, let's say psi n of x. Now, the set psi n doesn't form an orthonormal set. Is not orthonormal. Now, a set is said to be orthonormal if orthogonality between each and every single member of the set. So, here comes another set. Let's call it Bn, B sub n of x, where This kernel and this kernel are said to be bi-orthogonal because they satisfy the following property. The family of psi n, psi naught, psi 1, psi 2, psi 3 of x, and so on. And then we have beta family, beta naught of x, beta 1 of x, beta 2 of x, and beta 3 of x, and so on. Then beta 1 is orthogonal to psi naught, psi 2, psi 3, and so on. Beta 2 is orthogonal to psi 3, psi 1, psi naught, but not psi 2. So beta k, the correlation between beta k and psi n is equal to 0, that is, beta is orthogonal to psi if n is not equal to k, and some value, let's say capital A, we have to normalize it later, if n equal to k. So these two sets are bi-orthogonal if they satisfy. So if you wish to evaluate this coefficient associated with psi n, then you have to do a correlation between the function f of x that you wish to expand and beta n of x. So that's how a bi-orthogonal transform works. So I shall prove that this whole story was happening in Taylor series without us being knowing about it. But for the moment, let's just remind you of the method that we learned to evaluate the coefficients in Taylor series. The formula was simply a sub n equal to 1 over n factorial, and then the nth derivative of f of x while substituting x equals 0. And this formula can be simply understood if we took into consideration that we have assumed that f of x is equal to a0 plus a1 times x plus a2 times x squared plus a3 times x to power 3 plus a4 times x to power 4, and so on. And if you want to evaluate the coefficient a3, all you have to do is take the third derivative of f of x, that is, you are taking the derivative of both sides of this equation, so all these terms are going to be 0, and you take the third derivative, and after you substitute x equals 0, the higher terms are going to be equal to 0, and then you divide by 3 factorial to get a 3. So this is a fairly understandable geometric interpretation of Taylor series, but what I'm going bi-orthogonal transformation interpretation by proving that this familiar formula is actually similar to doing a correlation between the function and a bi-orthogonal set, which we will find out next. Now, the final stage after that long review. So, what I'm proposing is that the bi-orthogonal set to this non-orthonormal set is delta n of x, where n is the order of derivative of the impulse function. So I have to prove now that this set 1x, x squared, x cubed is bi-orthogonal with delta x, delta dash of x, delta double dash of x, delta triple dash of x. And we shall prove this step by step. First of all, let's have delta of x and correlate it with 1x, x squared, x cubed, and see what's going to happen. So, the correlation between delta x and 1 is obviously 1, which is the area under impulse function. So, they are not orthogonal. Let's see the correlation between delta x and x. The result is obviously 0, because if you multiply x with delta of x, you will get a 0 function. So they are orthogonal. And then delta x with x squared obviously the result is 0 again, because if you multiply x squared with delta of x, you'll get 0. So in general, that delta of x is always orthogonal to x to power n except for n equals 0. Now, let's see what about delta dash of x. First of all, delta dash with 1. So the correlation between them is obviously 0. That's easy to conceive because delta of x is an even function, and when you differentiated it, you get delta dash of x, then it will be an odd function, and the area under an odd function is 0. Then we have delta dash with x to power 1. By applying integration by part, we can easily find the result of this integration, minus 1. And then the correlation between delta dash and x squared will be 0. You can check that. So in general, we say delta dash is orthogonal with x to power n except for now we will write a more general statement. The nth derivative of impulse function is orthogonal to the kth power of x unless n equal to k. And an even more general statement, we say that the correlation, the cross correlation between nth derivative of impulse and kth power of x is given by minus 1 to power n times n factorial when n equal k and 0 when n is not equal to k. So that is a perfect biorthogonality between those two sets. So if Taylor claimed that f of x can be expanded according to this formula, summation an dot x to power n, where x to power n doesn't form an orthogonal set. Then according to the biorthogonality with delta n of x, a sub n, the coefficient, can be determined by a correlation between the function to be expanded f of x and delta n of x, and then of course normalized by this factor. And I shall prove now that this is Taylor had stated, which is 1 over n factorial nth derivative of f of x when substituting x equals 0. To prove this, first of all, I'd like to mention that taking the first derivative of a function is equivalent to convolve the function with delta dash of x by convolving f of x with delta of x. This will give you f of x again, because taking the Fourier transform of this equation, f of x have a transform of f of f, and delta of x has transform of 1, and convolution will be substituted by a dot product, then f of f times 1 is f of f again, so the result of convolution is f of x. Now, if we convolve f of x with the first derivative of impulse, so we are multiplying f of f by j, which is basically correspondent to the first derivative of f of x. So we can write a general statement: a convolution between f of x and nth derivative of the impulse function is equal to the nth derivative of f of x. Now, by evaluating this convolution, which is defined by integration nth derivative of delta evaluated at x minus lambda dot f of lambda d lambda. And then what Taylor did after he evaluated the nth derivative, he substituted x equals 0. So I'm going to substitute x equals 0. So this will be 0, and we end with this. And then by understanding the nature of even odd property of impulse function while taking subsequent derivatives, you can simply deduce that the nth derivative of delta evaluated at minus lambda is equal to minus 1 to power n nth derivative of this integral lambda. Simply represents the correlation between nth derivative of delta and f. So that replaced by a correlation, and this is minus 1 to power n. And then this is equal to the left-hand side, which was the nth derivative of f of x substituted, evaluated at x equals 0. So now we have this definition copied here, okay, and then we replace this correlation by its value determined from this equation, which is nth derivative evaluated at x equals 0 divided by minus 1 to power n. Here it is. And then we'll have this, and this eliminated. And we will end up very same definition of Taylor series coefficient. So that's it. Done and done. Goodbye and thanks for watching.